we have seen that in a 3-phase core type transformer, both the high and the low voltage windings are wound on the same core. The arrangement is somewhat like this. This is the transformer core. I am drawing a 3 core type arrangement, 3 limb type arrangement rather. The high voltage and low voltage windings, let us say this is the HV winding, this is the LV winding, of a particular phase. Similarly, for the other phases, the individual windings may be connected in star, delta or zigzag or whatever. However, in steady state with balanced sinusoidal supply, each of this set of winding operate independently of each other. This can be understood as follows. For example, let us say this is phase A winding, this is phase B winding and this is phase C winding. Irrespective of the connection of the individual windings, with balanced 3-phase voltage applied between lines, the winding voltages will also be balanced and will have the same phase sequence as the line voltage. So, let us say the high voltage winding is excited. In this particular case, this is the high voltage winding voltage V A phasor, this is V B phasor and this is V C phasor. Assuming ideal transformer, the flux produced by the high voltage winding is phi A, phase B is phi B and phase C is phi C, which lags the respective applied voltage by 90 degree. So, this is phi A, this is phi B and this is phi C. Now, each of these voltages will divide in 2 equal parts, assuming negligible reluctance of the core. One will flow through this one part, the other part will flow through this. Similarly, for the other phases. So, the net flux flowing through limb A is phi A minus half of phi B plus phi C. However, from this phasor diagram we see that phi B plus phi C is nothing but minus phi A, because these fluxes are also balanced. So, this is equal to phi A minus half of minus phi A. This is equal to 3 by 2 times phi A. So, phi A net. Therefore, the net flux linking the HV and LV winding on each phase leg is in phase with the flux produced by that particular winding, it is in fact proportional. Therefore, with balanced 3 phase supply voltage, each of these phases operate independent of each other, that is, each set of HV and LV winding can be treated separately irrespective of their connection, provided we know what are the applied voltages and the currents. That being the case, it is possible at least to do steady state analysis with balanced supply with the 3 phase transformer on per phase basis. That is, given a transformer, we find out first what are the applied winding voltage and winding currents, and then proceed in the same manner as that of a single phase transformer. For example, let us take this as an example. Let us say we have a Y D connected 3 phase transformer. This is supplying. So, Y D connected 3 phase transformer. This is the high voltage side connection. And this is A, this is B, this is C. This is the low voltage side. B, A, C. Suppose the applied line to line voltage on the high voltage side is V L and the load current on the low voltage side is I L at an angle phi L. Now, it should be understood that when the phase angle of the load current is specified, it is with respect to the line phase angle of the line current with respect to line to neutral voltage, not line to line voltage. So, if we want to convert it into per phase equivalent circuit, then what is the applied phase voltage on the HV side? V phase on the HV side. This is equal to V L by root 3. Similarly, what is the line current through the LV side, phase current through the LV side? I phase LV, magnitude is I L by root 3. What about the phase angle? For that, let us see the LV side voltage phasor, line to line voltage phasor diagrams are like this. This is line current I A, this is I B, this is I C. So, this is winding current, this is winding current, this is winding current I A B, I B C, I C A. Now, as I said, the line to neutral voltages are these. This is the neutral point. So, this I L, let us say, is at a lagging angle of phi L. This is say I A. Similarly, this will be I B, this will be I C. So, what will be the winding currents? Let us see. So, line current I A can be written as I A B minus I C A. Similarly, I B can be written as line current I B equal to I B C minus I A B, and I C can be written as I C A minus I B C. So, if we draw the phasor diagram, we see that this is line current I A. This can be drawn as I A B minus I C A. So, the angle between, if the line voltage A B leads the line to neutral voltage V A by 30 degree, then line current I A B, angle between line current I A B and voltage I A B, voltage V A B will be same as the angle phi L. This can be shown. So, the LV side line current, LV side winding current is also at an angle of phi L. With this, now it is easy to draw the equivalent circuit of the transformer, because with the winding voltage and the winding current specified, this set of winding can be treated as a single phase 2 winding transformer. And we already know the equivalent circuit for that. The approximate equivalent circuit will be this is applied voltage V phase per phase core loss component, core loss resistance. This is per phase magnetizing reactance, per phase equivalent series resistance, per phase equivalent leakage reactance, and the current here is, this is the low voltage side phase voltage V, this is high voltage side phase voltage V phase, this is low voltage side phase voltage V phase, and the current I phase is at an angle phi L. Hence, following the same procedure as we have used for single phase transformer, we can find out what will be the voltage V phase, what will be the input line current I phase, what will be the per phase magnetization, per phase no load current I 0 phase, magnetization current and core loss current. All these in per phase basis we will be able to find out following the same method as that in a single phase transformer. Once we have them, then we go back to the original connection of the transformer. We know that the low voltage side is delta connected. So, the low voltage side line voltage will be same as the phase voltage. So, low voltage side line voltage will be same as the phase voltage. However, low voltage side line current is not same. On the high voltage side, we have seen that the high voltage side is star connected. So, high voltage side line current I L will be same as I phase and all other the line quantities. So, no load line current will be same as referred to the high voltage side, it will be same as the no phase current and also these two components. So, this is how a 3 phase transformer can be analyzed on per phase basis using the same per phase equivalent circuit as that of a single phase transformer. Now, we have seen with single phase transformer, in order to analyze a transformer using this equivalent circuit, we need to know the parameters of the equivalent circuit. And in order to find this parameter, we performed no load and short circuit test. The similar tests are to be carried out for 3 phase transformer as well. So, for a 3 phase transformer, how the no load test circuit will look like? For the same transformer, let us say the no load test is usually done on the low voltage side, and in this case the low voltage side is delta connected. So, you have this delta connected transformer. Delta connected low voltage side, the high voltage side is star connected and kept open. This is kept open. Voltage is applied to the low voltage side. In order to measure the line current, a ammeter is connected and also an wattmeter. And here you apply rated 3 phase voltage, rated low voltage side 3 phase voltage, maybe through a variac. rated line to line 3 phase voltage is applied here. There are two, the power is measured using 2 wattmeter method and the line voltage is also measured. So, as in the case of a single phase transformer, the no load test will yield 3 readings: no load voltage, this will be line to line voltage VLL, no load current, IL, and the no load power, no load 3 phase power. This will be given by, for 2 wattmeter method, it is reading of W1 plus W2. Now, depending on the transformer connection, this is delta connected, therefore, the no load applied phase voltage is VLL by root 3, no load phase current, the phase voltage is same as VLL, sorry, this is same as phase voltage, phase current is IL by root 3, this is equal to I phase, no load phase or winding current, and the no load power is, phase power is W1 plus W2 by 3, this is equal to W phase. So, once we have converted this no load test data to phase quantities, then this can be used in a similar manner as that in a single phase transformer to find out the shunt branch component of the per phase equivalent circuit, that is R0 and Xm. The procedure, as we have seen, is that the no load power factor cos phi 0 equal to no load power per phase divided by no load phase or winding voltage multiplied by no load phase current. Once we know cos phi, then we know the Rm or R0 equal to V phase divided by I0 or I phase cos phi 0 and Xm equal to V phase divided by I phase to sin phi 0. So, this gives the shunt branch component of the per phase equivalent circuit of a 3 phase transformer. In order to find the series branch parameters, that is Req and Jxeq, we will have to carry out the short circuit test. Short circuit test is done on the high voltage side. Therefore, it is the high voltage side that will be connected and the low voltage side will be short circuited. Low voltage side will be short circuited. The high voltage side will be connected through again 2 wattmeters and a ammeter. This will be supplied from what we call a 3-phase variac in order to control the current flowing into the line. Here again and a voltmeter will measure the line to line voltage. Here again the readings that will be taken are line to line voltage. The variac will be adjusted such that rated line current flows through the high voltage side, then we will measure line to line voltage, should be VLL. The line current IL and 3-phase power equal to W1 plus W2. These we will convert to phase values again. So, this is star connected. So, V phase will be equal to VLL by root 3 star connected. Therefore, I phase is same as I line and per phase power W phase equal to W1 plus W2 by 3. Once we know the phase voltage, current and power, then we proceed in the same manner as that of a single phase transformer to find out the per phase equivalent circuit parameter, that is ZEQ is obtained as V phase by I phase, REQ is obtained as W phase divided by I phases square, and XEQ is obtained as square root of ZEQ square minus REQ square. However, it should be appreciated that the values of REQ, ZEQ, REQ, XEQ obtained like this refers to the high voltage side, whereas the shunt branch parameter that were determined from the no load test are referred to the low voltage side. Now, all the parameters have to be transferred to either high voltage side or low voltage side depending on the analysis requirement. For example, the series branch parameter can be converted to the low voltage side by the following relationship, that is ZEQ dash with refer to the LV side will be equal to NLV by NHV square into ZEQ. REQ dash will be equal to NLV by NHV square into REQ. XEQ dash will be equal to NLV by NHV square XEQ. Alternately, all the parameters may be expressed in per unit form with the bases selected as the power base to be selected as a 3-phase power rating of the transformer, and the voltage bases from either side can be selected as the rated line to line voltage of the high voltage and low voltage side respectively. If you do that, then the parameters that we obtain can be used without further referring by turns ratio. In fact, the test data in themselves are sometimes specified in per unit terms, that is, when you are doing no load test, you can say that we applied 1 per unit line to line voltage. So, the line current was so many per units and the 3-phase power was so many per units. It can be easily shown that if the test data themselves are specified in per unit form, then the parameters that we will determine from the test data will also be in per unit, and in which case this again this converting to or referring to different sides will not be necessary. So, let us explain or try to solve a problem to show how a 3-phase transformer can be tested and analyzed. Let us see, let us take an example. We have a 11 kV by 400 volt 150 kVA 50 hertz delta Y connected 3-phase transformer. From the no load test, no load test data which was done on the LV side, that is on the Y connected side, is as follows. The line current is 10 ampere and the 3-phase power is 2 kilowatt, when rated applied line to line voltage is given. The line to line voltage is rated line to line voltage 400 volt. Similarly, the short circuit test data which is conducted on the HV side are as follows. The applied line to line voltage is 600 volts. This is again line to line voltage. the HV side here is delta connected, the line current is measured, the line current is 8 ampere and 3 phase power this is 3.5 kilowatt. So, let us try to find out the equivalent circuit parameter of this transformer. So, no load test is performed on the low voltage side, which is star connected. So, phase voltage is this is equal to 400 by root 3 equal to 230.9 volts, and line phase current equal to line current equal to 10 amperes. The no load power factor cos phi 0 is given by no load power 3 phase power divided by root 3 no load voltage line voltage into line current comes to be 0.289. Therefore, phi 0 comes to be approximately equal to 73.2 degrees. With this, so let us find out R 0. So, this will be referred to LV side. This is found as V phase divided by I phase cos phi 0, that is 230.9 divided by 10 into 0.289, this comes to 79.91 ohm. XM per phase referred to LV side. XM referred to LV side will be V phase divided by I phase sin phi 0, this comes to 24.12 ohm. So, the shunt branch parameters referred to the LV sides are found this way. Let us now try to find out the series branch parameter from the short circuit test. This is referred to HV side and HV side is delta connected. So, HV side phase voltage SC test from short circuit test equal to VLL equal to 600 volts, HV phase current equal to IPH equal to IL by root 3, that is 8 by root 3, this is equal to 4.62 amperes. Therefore, Z dq refer to the HV side equal to V phase divided by I phase equal to 129.9 ohm. Req refer to HV side equal to 3 phase per phase power So, 3 phase power is 3.5 into 10 to the power 3 divided by 3 into this is 3 phase power into 8 by root 3 square, that is 3.5 into 10 to the power 3 divided by 8 square equal to, this comes to 54.69 ohm. X eq HV side equal to square root Z eq square minus R eq square equal to, this comes to 117.83 ohm. Now, these are referred to HV side. However, the R0 and Xm were referred to LV side. Now, converting the Req and Xeq referred to the LV side, then for that we need to know the turns ratio N HV by N LV. This is equal to HV side is delta connected. So, phase voltage and line voltage are same. So, this is 11 kV. LV side is star connected. So, the phase voltage is 400 by root 3. This comes to 47.63. Therefore, Req dash equal to Req into N LV by N HV square equal to Req divided by N square. This comes to 0.0241 ohm. Similarly, Xeq dash comes to Xeq by N square, this comes to 0.052 ohm. Therefore, the per phase equivalent circuit referred to LV side, which is star connected, will look like this. This is the applied voltage V p dash, this is R 0, the value is this value is 79.91 ohm, this is J 24.12 ohm, this is R eq dash equal to 0.0241 ohm, this is x eq dash equal to J x eq dash equal to J 0.052 ohm. This is where is the secondary phase voltage, the secondary line current, which is same as secondary phase current, because secondary side is delta connected, and secondary line current, because secondary side is star connected, low voltage side is star connected here. This is the high voltage side phase current I phase. Now, given a load condition, this problem can be now analyzed. Let us see a particular example. Let us say that this transformer is connected on the LV side to a balanced load that draws full load current on LV side. It is connected to a balanced load which draws, that is on the LV side I L equal to full load current at a power factor of 0.85 lagging. On the HV side, let us assume this is connected to a 11 kV 50 Hertz source. Now, let us try to find out the line voltage on the LV side under this operating condition. Now, from the given data and referring to this equivalent circuit, V p dashed equal to 11 kV divided by the high voltage side is delta connected, therefore, phase voltage is same as line voltage, 47 divided by turns ratio equal to 230.94 volts. On the low voltage side, which is star connected, full load current is flowing, and no voltage side is star connected. So, line current is same as phase current. So, I p equal to 150 kVA, which is the rated kVA of the transformer, divided by rated root 3 into rated line voltage. This is equal to 216.5 amperes, and cos phi equal to 0.85, giving phi equal to 31.8 degrees. Now, as in the case of a single phase transformer, we can draw the phasor diagram. Let us say this is V p and this is I p, then this is I p R e q dash, this is V p dash, this is V p, this is I p R e q dash, this is I p x e q dash. Now, this angle is delta. Usually, this delta angle in a transformer is very small. Therefore, we can write V p is approximately equal to, is actually equal to V p dashed cos delta minus I p into R e q dash cos phi minus x e q dash sin phi. Since delta is approximately equal to 0, cos delta is approximately equal to 1, therefore, V p equal to comes to from this formula about 220.57 volts, and hence the low volt L V line voltage equal to root 3 V p equal to 382.05 volts. In a similar manner, one can find out also the no load current and the input current, phase current I p dash. Thank you.